In physics. If physical phenomena are due to motion, it is to the motion of molecules which we cannot see. If, then, the acceleration of bodies we cannot see depends on something else than the positions or velocities of other visible bodies or of invisible molecules, the existence of which we have been led previously to admit, there is nothing to prevent us from supposing that this something else is the position or velocity of other molecules of which we have not so far suspected the existence. The law will be safeguarded. Let me express the same thought in another form, in mathematical language. Suppose we are observing n molecules, and find that their 3n coordinates satisfy a system of 3n differential equations of the fourth order, and not of the second as required by the law of inertia. We know that by introducing 3n variable auxiliaries, a system of 3n equations of the fourth order may be reduced to a system of 6n equations of the second order. If, then, we suppose that the 3n auxiliary variables represent the coordinates of n invisible molecules, the result is again conformable to the law of inertia. To sum up, this law, verified experimentally in some particular cases, may be extended fearlessly to the most general cases, for we know that in these general cases it can neither be confirmed nor contradicted by experiment. The law of acceleration. The acceleration of a body is equal to the force which acts on it divided by its mass. Can this law be verified by experiment? If so, we have to measure the three magnitudes mentioned in the enunciation: acceleration, force, and mass. I admit that acceleration may be measured, because I pass over the difficulty arising from the measurement of time. But how are we to measure force and mass? We do not even know what they are. What is mass? Newton replies, the product of the volume and the density. It were better to say, answer Thomson and Tate, that density is the quotient of the mass by the volume. What is force? It is, replies Lagrange, that which moves or tends to move a body. It is, according to Kirchhoff, the product of the mass and the acceleration. Then why not say that the mass is the quotient of the force by the acceleration? These difficulties are insurmountable. When we say that force is the cause of motion, we are talking metaphysics, and this definition, if we had to be content with it, would be absolutely fruitless, and would lead to absolutely nothing. For a definition to be of any use, it must tell us how to measure force, and that is quite sufficient, for it is by no means necessary to tell what force is in itself, nor whether it is the cause or the effect of motion. We must therefore first define what is meant by the equality of two forces. When are two forces equal? We are told that it is when they give the same acceleration to the same mass, or when acting in opposite directions they are in equilibrium. This definition is a sham. A force applied to a body cannot be uncoupled and applied to another body, as an engine is uncoupled from one train and coupled to another. It is therefore impossible to say what acceleration such a force, applied to such a body, would give to another body if it were applied to it. It is impossible to tell how two forces which are not acting in exactly opposite directions would behave, if they were acting in opposite directions. It is this definition which we try to materialize, as it were, when we measure a force with a dynamometer or with a balance. Two forces, F and F prime, which I suppose for simplicity to be acting vertically upwards, are respectively applied to two bodies, C and C prime. I attach a body weighing P first to C and then to C prime. If there is equilibrium in both cases, I conclude that the two forces F and F prime are equal, for they are both equal to the weight of the body P. But am I certain that the body P has kept its weight when I transferred it from the first body to the second? Far from it. I am certain of the contrary. I know that the magnitude of the weight varies from one point to another, and that it is greater, for instance, at the pole than at the equator. No doubt the difference is very small, and we neglect it in practice, but a definition must have mathematical rigor. This rigor does not exist. What I say of weight would apply equally to the force of the spring of a dynamometer, which would vary according to temperature and many other circumstances. Nor is this all. We cannot say that the weight of the body P is applied to the body C, and keeps in equilibrium the force F. What is applied to the body C is the action of the body P on the body C. On the other hand, the body P is acted on by its weight, and by the reaction R of the body C on P, the forces F and A are equal, because they are in equilibrium. The forces A and R are equal by virtue of the principle of action and reaction, And finally, the force R and the weight P are equal because they are in equilibrium. From these three equalities, we deduce the equality of the weight P and the force F. Thus we are compelled to bring into our definition of the equality of two forces the principle of the equality of action and reaction. Hence this principle can no longer be regarded as an experimental law, but only as a definition. To recognize the equality of two forces, we are then in possession of two rules: the equality of two forces in equilibrium, and the equality of action and reaction. But as we have seen, these are not sufficient, and we are compelled to have recourse to a third rule, and to admit that certain forces, the weight of a body for instance, are constant in magnitude and direction. But this third rule is an experimental law. It is only approximately true, it is a bad definition. We are then reduced to Kirchhoff's definition: force is the product of the mass and the acceleration. This law of Newton in turn ceases to be regarded as an experimental law, it is now only a definition. But as a definition it is insufficient, for we do not know what mass is. It enables us, no doubt, to calculate the ratio of two forces applied at different times to the same body, but it tells us nothing about the ratio of two forces applied to two different bodies. To fill up the gap, we must have recourse to Newton's third law, the equality of action and reaction, still regarded not as an experimental law, but as a definition. Two bodies, A and B, act on each other. The acceleration of A, multiplied by the mass of A, is equal to the action of B on A. In the same way, the acceleration of B, multiplied by the mass of B, is equal to the reaction of A on B. As, by definition, the action and the reaction are equal, the masses of A and B are respectively in the inverse ratio of their masses. Thus is the ratio of the two masses defined, and it is for experiment to verify that the ratio is constant. This would do very well if the two bodies were alone and could be abstracted from the action of the rest of the world, but this is by no means the case. The acceleration of A is not solely due to the action of B, but to that of a multitude of other bodies, C, D, etc. To apply the preceding rule, we must decompose the acceleration of A into many components, and find out which of these components is due to the action of B. The decomposition would still be possible if we suppose that the action of C on A is simply added to that of B on A, and that the presence of the body C does not in any way modify the action of B on A, or that the presence of B does not modify the action of C on A. That is, if we admit that any two bodies attract each other, that their mutual action is along their join, and is only dependent on their distance apart; if, in a word, we admit the hypothesis of central forces. We know that to determine the masses of the heavenly bodies we adopt quite a different principle. The law of gravitation teaches us that the attraction of two bodies is proportional to their masses. If r is their distance apart, m and m' their masses, k a constant, then their attraction will be the quantity k m m' divided by r squared. What we are measuring is therefore not mass, the ratio of the force to the acceleration, but the attracting mass, not the inertia of the body, but its attracting power. It is an indirect process, the use of which is not indispensable theoretically. We might have said that the attraction is inversely proportional to the square of the distance, without being proportional to the product of the masses, that it is equal to F divided by r squared, and not to k m m'. If it were so, we should nevertheless, by observing the relative motion of the celestial bodies, be able to calculate the masses of these bodies. But have we any right to admit the hypothesis of central forces? Is this hypothesis rigorously accurate? Is it certain that it will never be falsified by experiment? Who will venture to make such an assertion? And if we must abandon this hypothesis, the building which has been so laboriously erected must fall to the ground. We have no longer any right to speak of the component of the acceleration of A which is due to the action of B. We have no means of distinguishing it from that which is due to the action of C, or of any other body. The rule becomes inapplicable in the measurement of masses. What, then, is left of the principle of the equality, of action and reaction? If we reject the hypothesis of central forces, this principle must go too. The geometrical resultant of all the forces applied to the different bodies of a system, abstracted from all external action, will be zero. In other words, the motion of the centre of gravity of this system will be uniform and in a straight line. Here would seem to be a means of defining mass. The position of the centre of gravity evidently